So other than Taylor series, do you have any other, you want to be any more specific, or you want me to just use my judgment?
Yeah, I was just like a general example problem, I guess.
Okay. And then Shannon's asking for a radius or a ratio test example.
Have
So-
you been a TA for this class? You've given this test out before, right?
I have, yeah.
Do you recall what students had the most trouble with, like when they got test results back? Did we go over that sort of thing?
Almost always, I mean, whether it's this subject or anything else, it's just I think everything boils down to how well you understand the concepts. So, and I think Mark has given that as well. So I would just you're going to have to know when to use certain tests. But really beyond that, understand why they work. Like, so the P series test. It's one thing to know that, all right, if P is greater than 1, it converges. If P is 1 or less, it diverges. But you might want to think about why that's been the case. Just based on examples we've done. Things like that. The geometric series, why does that converge? You know, you have a test for when a geometric series converges. Why does it make sense that that condition works? And for example, what other test is built based on that idea? So let's get an answer to that question. So the geometric series test, how do you know if a geometric series converges? And this is not just this is for the whole room, not anybody in particular.
If R is between -1 and 1.
Right. And just to be clear, what does that R stand for? What does that R mean?
It would be like the constant multiple.
Yes, that constant multiplier, rate of change, common ratio. You've probably heard it called a few different things. But yeah, that thing has to be between -1 and 1. All right, so let's do this. So I want to find a Taylor series. So find a Taylor polynomial. Let's say degree 3 for f of x equals natural log of x. And x equals 2. Or I guess he's calling it a, whatever, the center point is equal to 2. So let's just build this up. So I want to find this Taylor polynomial. That should be a 3. Based on this function, how would I go about doing this?
I guess like first step is just to find derivatives of the function given.
Good. So I have a function. Let's find that first derivative. What is the first derivative of natural log of x? Okay, Gabriella says 1 over x in the chat, or x to -1. All right, what's the next derivative? What's the second derivative of natural log of x?
-2x to the, no, wait. It would just be -x to the power of 1.
Not to the power of 1.
To the power of -2.
Right. Remember, when you take a derivative, the powers
yeah.
decrease. And then, let me be consistent here. -1 over x squared or negative x to the -2. All right, I want third degree polynomial, so I'm done. Or am I done? Do I need any more derivatives, or is this what I need?
I think maybe you would need one more.
Yeah, we do. So, and this is one thing I feel like it's a little bit lost. A third degree polynomial, how many terms could that have? I mean, there's a maximum. It could have less than that, but what's the most number of terms this might have?
4.
It could have 4 terms. All right, so I need a third derivative. So what's my next derivative of natural log of x?
+1 over x to the 3.
Very close. Anybody else want to modify that?
I think we're missing a 2 in the denominator.
Yeah, it should be +2 over x cubed.
Oh, fine.
Yep. So yeah, if we look at our second derivative, -x to the -2, yeah, multiply the coefficient by that -2, so you get +2 x to the -3. All right, now I think we're all set. So we have all the derivatives we'll need, at least all the expressions for them. Now what do we want to do? Okay, Gabriella says find the coefficients. Good. And how do we do that?
I was a little bit confused about like the coefficient part. So just like to confirm, like the coefficient would just be like so like for example, one of them could be like the first derivative with like 2 plugged in, like over 2 factorial, but
Yeah. So
just
let's look at a third degree Taylor polynomial here. So the first term is pretty easy. What's the first term going to be? So I'll kind of word it the way that Mark does. If you have a Taylor polynomial and it only has one term, what is that term going to get right about the function? Like, what is the only thing it's going to agree with the function on?
Just at the 1 point.
Right,
It's
it's just
just
gonna-
going to get you the one answer.
It's just going to have that point correct. So this will be f of a. If I include a second term, then it will get that point correct. And what else will it get correct?
The constant rate of change at that point.
Right, so it'll get that derivative right. So that'll be f prime of a. And then if I build this up, yeah, so then the third, if I have a second degree polynomial, I'll get the point correct, I'll get the first derivative correct, and I'll also get the second derivative correct. And I really should not be calling this just x. This should be x minus a. This next one should be f double prime of a times x minus a squared. And then if I continue that pattern to get one more term, f triple prime of a times x minus a cubed. How do we feel about this?
Yeah, agreed.
There's something missing that I intentionally left off.
they're divided by like n factorial.
Yeah, so basically, first two aren't going to make any difference. But really what you have is this. You're always dividing by whatever that power is. Whatever the power on x is, that factorial. And I'm not going to go through it again unless unless some of you really want me to, but think about what happens if you take the derivative of this function. Basically, the first derivative is going to make this term vanish. Then the second derivative is going to make this term vanish. But the second derivative of, let's say this term, that's going to come out to be 2 times f double prime of a, because of the way the power rule works. So because of that, we have to divide by 2 to make sure that we're really being faithful to the value of that derivative there. So that's why those factorials show up there. So now this is what our template looks like. So now we can start filling things in. So remember we said our a was 2. So what's that first term going to be?
F of 2 or ln of 2.
Yep, natural log of 2. All right, then the second one.
Is it ln half times what's x minus 2?
So I have the natural
Over
log of a half times x minus 2. And yeah, it would be over 1, but I'll just leave that off for now. Are we okay with this?
Wouldn't it just be 1 over 2 times x minus 2?
Yep, and that's one thing I wanted to point out here is just to be careful about 1/2 times x minus 2. So over here, we have, the function and the derivatives. So here's one thing I might recommend doing. On the left here, these are all general. So general. And over here, the general function and the derivatives are all, you need them. But really what you need to complete this Taylor polynomial is all these specific evaluations of it. So I want f prime of 2, which is going to be 1/2. What's f double prime of 2? And while we're at it, we'll get the f triple prime of 2. So these over here are going to be variable. And these over here are going to be constants, because I'm going to evaluate them x equals 2. Allison says -1 over 2 squared, which is going to be, yep, -1 over 4. And then finally, f triple prime of 2. 2 over 8, which will eventually become 1 over 4. So now I think we have even more of the pieces we need to finish this. And I'm going to rewrite a couple of things here just like that. So natural log of 2 plus x minus 2 over 2. What's that next term going to look like?
-1 over 8 times the square of x minus 2.
Yep. So there's your third term, and the last term is going to be basically 1/4 divided by 6. So that's going to be plus x minus 2 cubed over 24. Any questions about that Taylor series there?
Are we always given the A value?
Yeah, you'll need to be. Yeah, it's one thing I want to point out though. Let's say I would have replaced this word Taylor with the word Maclaurin. If I ask you for a Maclaurin polynomial, do I have to give you the center point?
No,
No. Why not?
The
'Cause it's
center point's
always
going to be 0.
Right. So by definition, a Maclaurin series is just a special case of a Taylor series. It's the specific Taylor series where the center point is 0. All right, that was a good question. And then I had a request for a ratio testing to find an interval of convergence. So I'll let you know, I'm not sharing the other screen where I'm doing this, but really the place where I got that last example and the place where I'm going to get this new example is really all I Googled for that last one was Taylor expansion example or Taylor series example. If you search for examples online, you'll find over and over this Paul's online math notes. And I really recommend going to those pages because they have lots of examples where the solutions are hidden until you want to look at them. So they're really good for a checking to make sure that you're on the right track, and you basically lets you take a crack at it before they give you the answer. So for this one, I'm sorry, what was that?
Sorry to interrupt. I was going to ask about the. I must have forgotten how factorials work. Could you really quickly explain how that happened there?
Of course. Basically, so if I have a number, let's just do an example, a big enough example you can see what's happening. 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1. So basically, it's only valued for integers, for positive integers. Sorry, non-negative, because 0 factorial is well defined. But basically, just take that number and multiply it by all the integers, all the way down to 1.
So how did 2 factorial become 8?
It didn't.
Oh, okay.
2 factorial is 2. But remember, the second derivative at the point that we cared about was -1/4. So basically, -1.
Oh, gotcha. Okay, thank you.
Yeah, no problem. Yeah, -1/4 divided by 2. All right, so interval of convergence example. Again, Paul's online math notes. All right, let's do this example here. Want to find the interval of convergence for this guy from n equals 1 to infinity of x to the 2n over -3 to the power of n. So I want to find the interval of convergence for this. So what should I do first? So, okay, Gabriella says use the ratio test, which absolutely will do. So I want the limit as n approaches infinity of this ratio here. And since somebody asked, what are the biggest pitfalls for this? And I said, basically for any topic, it's the concepts. Not it's important to know what to do, but it's also important to know why you're doing it. So can someone explain to me, like, why do we use the ratio test? Why am I using this limit for this ratio between 2 consecutive terms?
Because it's kind of difficult to tell like where this like series would converge. by
Right.
just looking at it. So if you use the test, you could see like where it converges more easily.
Okay. And why does this make it easier to think about where it converges? And I
Because
think,
like terms will be canceled out.
yeah, terms will be canceled out. So one more thing I'm going to say here is, all right, the ratio test, your series converges if this ratio is less than what?
Less than 1.
Less than 1. Why is that? Where does that number 1 come from?
Because we're trying to see what this would look like when it gets really big, if it's going to look like a geometric series or not.
Right, and that's what I was getting at. So the whole motivation for the ratio test is, I'm hoping that as n gets really, really big, you know, somewhere down the line, this series is going to essentially become a geometric series with some constant multiplier. Obviously, for small values at n, that's not going to be the case. But if we go out far enough, we might be able to approximate that. And we understand a lot more about geometric series than we do about, you know, whatever kind of series this is that we're looking at. So if we can make an argument for this thing looking like a geometric series, we can have a better idea of when it converges. All right, so here is the ratio test. Let's go ahead and start dropping things in. So I'm going to have x to the 2n. Actually, you tell me what to write here.
On the top would be x to the 2 parenthesis n plus 1.
Good.
And
on.
then divided by -3 to the n plus 1 power.
Good. And then basically just multiply that by the reciprocal of what I was given. So x to the 2n. All right, and I want this thing to be less than 1. All right, where can I go from here?
We simplify the top and bottom.
Okay, and if I simplify, what will this look like?
On the left side, x is gonna, yeah, we'll just have like x to the power of 1.
I don't think it's going to be x to the power of 1.
Oh, plus 2. Oh, x to the power of 2, sorry.
Yeah, so let's break this out over here. X to the 2n plus 1 over x to the 2n. That's going to be x to the 2n plus 2 over x to the 2n. So eventually that'll become x squared. So back over here, I'll have x squared in the numerator. And what will I have in the denominator?
Just
Another
negative.
-3.
-3, just 1. And I want that to be less than 1. Are we okay if I do this? So absolute value of -3 is just going to be 3. So basically now the ratio I'm solving for is -1, which is less than x squared over 3. It's less than 1. So I have -3, which is less than x squared, which is less than 3. And I actually don't know if Mark has had you do one like this before where we're dealing with he's had you do quite like you have like an x squared at this point, right? Okay. All right, so what do I do from here?
Wouldn't it be plus or minus the square root of both sides?
Yeah. And I'm going to go ahead and, if you're okay with it, I'm going to go ahead and modify this a little bit because I know that Mark has not had you deal with one where you're going to have to deal with imaginary numbers. So I'm going to change the x out for x plus 5. Is that what I want to do? Yeah. So x plus 5 to the 2n. And I'm just realizing I should have done minus. All right, this should be a little easier to deal with now. So from here, actually, that's not the problem. I'm sorry, I'm gonna go ahead and punt on this one and go for one that I know works. And I'll fast forward it. I'll fast forward a bit to the part where I know that we need to review. So let's look at this series instead. So as n goes from 1 to infinity, 1 to the n times n over 4 to the n times x plus 3. So I'll just speed up the ratio test again. All right. So hopefully you can see how I got to where we are now. So let's take it from here. How would I continue?
Do you mind if we like come back to like how you simplify really quickly after we finish the problem?
Yeah, let's do it right now, actually, because like I said, I fast forwarded here. So let me go ahead and take out a lot of these crosses. All right, so let's talk about how this thing gets simplified. And really, and a lot of things should cancel because what you're doing is you're looking at consecutive terms. So anywhere where you're dealing with powers of n, you're going to be canceling out all but one, usually all those powers. So the first thing I'm going to look at is I have -1 to the n plus 1 in the numerator and -1 to the n in the denominator. So what's going to be left and where's it going to be?
Do we want to split this into 2 parts to sort of break it down?
What do you mean by that?
Like on one side, the limit of n plus 1 over 4n plus the limit of x plus 3 on its own.
Oh no, so let me get rid of this for a second. Right now I'm backing up to the step where we're basically simplifying this nasty looking expression here.
Oh, okay.
So was it helpful to like rewrite the expression so that like what you want to cancel out is like numerator denominator, like closer to each other rather than like.
Yeah, I mean, if that helps you, then absolutely. So let's do that. So -1 to the n plus 1, and right underneath it, we'll put -1 to the n. Then I have n plus 1. Right underneath it, we'll put n. Then we have x plus, actually, I'm going to leave the x for the far right. So then we'll have 4 to the n over 4 to the n plus 1. And then finally, x plus 3 to the n plus 1 over x plus 3 to the n. So yeah, if it helps you think about this to organize it better, to do that, then yeah, absolutely, it's a good move. So from here, what cancels? Or what's left is the more important question.
This is where I basically get tripped up every time. Like I try to look for a pattern like in the homework, but I don't consciously know what I'm doing.
First, you would look at the alternating -1 over the -1. You'd simplify that down either to 1 or -1. Then see that, hey, this is an absolute value, so it doesn't matter.
Okay, so for right now, I'm just going to leave it as -1.
Yeah.
And I want to do a note off to the side here based on Casey's question. So let's do this. X to the 7 divided by x to the 4th. So when you see something like that, how do you simplify that?
You use like the exponent rules and you just subtract the powers.
Right, so that's x to the 7 minus 4 or x cubed. And even though you have, variables in your exponent here, you can do the same kind of thing. So if I have -1 to the n plus 1 over -1 to the n, that's the same thing as -1 to the n plus 1 minus n, which is -1 to the n. No, it's not. It's -1 to the 1. On the other hand, if you have something like this, which we do, 4 to the n over 4 to the n plus 1, that's the same as this, 4 to the n minus n plus 1, which gives you 4 to the n minus 1, or 4 to the -1. And 4 to the -1 is the same as what?
1/4.
1/4. So that tells me that, that 4 to the n over 4 to the n plus 1, you're going to be left with a 1 in the numerator and a 4 in the denominator. Which is a little bit different than the way that Mark usually leads you all through that, but never hurts to have another way to look at it. What is going to cancel out with the n plus 1 in the end?
It will just become like basically 1 since they both have the same like degree for the leading term.
So the limit, yes, but really for right now, I can't really do any canceling with that. And then finally, the x plus 3, for the same reason as the -1, I'm going to have x plus 3 in the numerator and 1 in the denominator. So my limit here is going to be, and we're doing absolute values, so that -1 is going to become 1. So really what I have left is this, n plus 1 over n times x plus 3. Right. And I think
Isn't there a 4? Isn't there a 4 in the denominator too?
Yep, I just lost it. Yep, there it is. Thank you. All right, now what?
Is it not negative?
I took out the negative. Why did I do that?
Because it's absolute value.
Yeah, absolute value. So I know that negative is eventually going to become positive. So I essentially replaced the -1 with a +1.
Oh, that's what Rand said. Wait, why?
Well, think about what absolute value does.
Oh no, I know what absolute value is, but why are we saying absolute value?
So that's the way the ratio test works.
Oh, is that? Oh. Okay, yeah. The lines outside of the. Yeah.
Oh yeah,
gotcha.
So yeah, remember when you're doing the ratio
Gotcha.
test, because a lot of the times when you're doing a ratio test, you are dealing with things that alternate. So it'd be really nice if I could, find a way to just set that aside for the time being. And that's what the absolute values allow us to do. All right, so how can I handle this limit from here? Here's one thing I'm going to point out. Is it okay if I do this? Now, these things are all equal to each other. Is it okay if I pull out that x term all the way out of the limit like that?
Well, that would be okay because it's like the A in a geometric series, right?
Yeah, basically. See, and another way to think about it, I'm taking the limit as what does what.
As n approaches infinity.
Right. So that as n does something, that is not going to have any effect on that limit is going to have nothing to do with x plus 3. So I can just pull it out. All right. What is this? So now we can evaluate the limit, right? What is this thing going to go to? The n plus 1 over 4n. Okay, Gabriella says 1/4, and I agree with that. So x plus 3 absolute value times 1/4. So we're done now. I mean, we've evaluated this limit. But remember, we're doing the ratio test. So what do I need to keep? Like, what does this ratio have to have? What has to be true about it? I want it to be less than what? Less than 1. So from here, I have this absolute value. So I have, the absolute value of x plus 3 times 1/4 is less than 1. Or the absolute value of x plus 3 is less than 4.
I must have missed something. How did we simplify that?
Just to get to that last step there.
Mm-hmm.
Basically what I did was this. Multiply this by 4 and multiply this by 4. So that cancels out the 1/4.
Oh, sorry. I meant getting to 1/4.
Sure. So let's pull that off to the side here. And I'll explain this a couple different ways. One is, kind of Mark's preferred approach, but I'll give you an alternative. So n plus 1 over 4n. This is a rational function. I have a polynomial in the numerator and a polynomial in the denominator. How do those degrees compare?
They're the same.
They're the same, right? So since they're the same, what does that mean is going to happen to the entire rational function?
Did you divide both? You divided everything by n, right? And then.
So that's the other way I was going to show you. But basically,
okay.
I can say this: these functions are not the same, but I can say that these limits are the same. Because as n gets very big, that 1 is going to become less and less relevant, less and less significant. So basically, as n grows larger, that 1 is going to get overwhelmed. So essentially what you
Gotcha,
have
okay.
is a limit of 1/4, which is just 1/4. The way that I prefer to look at these, and this is just a more personal preference thing, is I know for sure that n plus 1 over 4n is equal to n over 4n plus 1 over 4n, which is equal to 1/4 plus 1 over 4n. If you think about the limit as n approaches infinity of this thing, hopefully it's clear that the 1/4 will never change, but the 1 over 4n will go to 0. So that's essentially the same as 1/4 plus 0. So however you get there, you're going to get a limit of 1/4.
Yeah, I like that one better.
Okay. Cool. All right. So from here, I'm done with the limit. I think I'm ready now to figure out what the interval of convergence is. So where do I go from here?
You would express that as -4 less than x plus 3 less than 4.
Yep. And then I can solve for x. Subtract 3, subtract 3, subtract 3. -7 is less than x, which is less than 1. So I'm getting really, really close to having my interval of convergence, but what else do I have to do before I'm totally done?
We have to test the values of -7 and 1 by plugging it back to
Good.
the
So
original.
right now what we know is this. Every x that's strictly inside that interval, like everything that's strictly greater than -7 or strictly less than 1, that'll be a convergent series. But what I have to do now is test the boundaries. So x equals -7 gives me this series. -1 to the n times n times -4 to the n all over n plus 1 times 4 to the n. So we're no longer dealing with a power series, we're just dealing with a series that is whose only variable is n. So how do I tell if this thing converges or diverges?
Would we do another like ratio test?
You could, but we don't need to here. Alternating series test. We can only do the alternating series test if this thing alternates, and I don't think we know if that happens yet. So I'll give you a way. Here's how you can simplify these things. And I'll go ahead and work in blue on the side here again.
I don't think it alternates.
Yeah, it's not going to. So let's figure out why. If I have -1 to the n times -4 to the n, that's going to be the same as this. -1 times -4, all raised to the n. No, it's not. -1 times -4, all raised to the n. Which, if I simplify that, just comes out to be 4 to the n. So now, going with that, I have 4 to the n times n over 4 to the n times n plus 1. And from there, I get the series n over n plus 1. Does this thing right here converge or diverge?
Wouldn't it just converge to 1?
When you say, does it converge to 1, what are you saying converges to 1? Be specific.
Like n over n plus 1?
Right. So is that the sequence or the series?
It would be the series.
Actually, n over n plus 1, that right there is just the sequence. So basically, what you're going to have is this. The limit as n approaches infinity of n over n plus 1, that's going to be equal to, the limit as n approaches infinity of 1 plus, oh, we actually can't do that. What is this limit going to be as n gets very big?
One.
It's going to be 1, right? So basically, we're going to have a series that as n gets very big, we're just adding 1s infinitely. So what can we say about this series when x is equal to -7?
So it diverges then?
It diverges. Because, so the sequence converges to 1. If you have a sequence that converges to 1, what can you say about the series?
It must diverge because the only time like a series can converge is if the sequence converges to 0.
That's absolutely correct. Yep. So yeah, if your sequence converges to something that's not 0, then your series must diverge. All right, so I have 351. I am going to go over basically the other boundary point, the x equals 1. If you want to stay for that, you're welcome to. Otherwise, you're free to go. The grade this week is just going to come from basically, I have a list of everyone who's here today. You'll get credit if you're here. I am going to email out these notes, and I'll let you know when these videos are posted. For anybody who wants to stay, I'll do the other part of this interval of convergence. Otherwise, I will see you all in class tomorrow morning. Okay, so now let's plug in 1 for x here. I'll scroll up a little bit so we can see what the series is. So that's going to be -1 to the n times n times 4 to the n over n plus 1 times 4 to the n. So someone who's still here, where do we go?
Wait, where do you get that equation from?
So this right here comes from this. And basically what I'm doing is plugging in my boundary conditions. So the two boundaries I got for the interval were -7 and 1.
Mm-hmm.
So basically I'm plugging in 1, or I'm plugging into that x right there.
Where does the n plus 1 on the denominator come from?
Oh, I'm sorry. I was getting confused with my... Why did I have that for the other side as well? Okay, that shouldn't have been there. I'm glad I'm still recording. I don't think that makes it, I think it still diverges, right? Yeah. So now I just have a series whose only term is n, right?
Yeah, that goes to
So that must diverge. I mean, if we're saying it diverges, if it diverged when all the values were essentially going to become 1, it'll certainly diverge if every term gets larger and larger. So -1 to the n times n times 4 to the n over 4 to the n. Okay, so what do we think about this one? How can we find out if it converges or diverges?
Well, it simplifies to an alternating series.
Okay, so it simplifies to an alternating series. Simplifies to -1 to the n times n. All right, now what? Is that going to converge or diverge? Tony says it diverges. So it alternates, but every term is going to get further away from the x-axis than further away from 0 than the previous. So this diverges as well. So our series converges for this interval. -7 is less than x, which is less than 1. And I cannot include either endpoint in that interval. Any last minute questions on that one?
And then the radius would just be the center between those 2 points of convergence?
Yeah, in fact, if all you're asked for is the center, we actually could have answered that question right here. So right there, the radius is equal to 4.
Okay.
But yeah, I mean, if you're asked for the interval, you have to go as far as we did. But yeah, the radius, yeah, you can either look at it as coming from the basically how far your endpoints are from your center, which that inequality, the absolute value of x plus 3 is less than 4. That also gives you.
So if it converges at the boundary, then the inequality sign would be less than and equals to, right?
Correct. Mm-hmm. All right, everyone. Have a good day. I'll see you in class tomorrow morning.